Assalamualaikum warahmatullahi wabarakatuh and very good day. So for chapter number 4, part number 7, we will discuss about the turbine blade cooling system. Okay, first we look at the introduction of the turbine blade cooling system, where in this figure shows the simplified cross-section drawing of a gas turbine engine. So we have three main components. We have a compressor, combustion chambers, and also a turbine. So in terms of mechanism that we have learned before, the compressor will compress the air, and the compressed air will enter the combustion chamber and mix with fuel. The combustion process will occur in the combustion chamber, where this combustion chamber, due to the combustion process, will produce exhaust gas, very hot exhaust gas. And this exhaust gas will flow through the turbine stage, where the fluid, in terms of kinetic energy of the fluid, will transfer to the rotor blade and then produce the rotational movement in the turbine, and the turbine will produce W out. So the important part, or the important point location when we discuss about turbine blade cooling system is the turbine inlet condition, where we know that due to the combustion process, this point, which is referred to the turbine inlet, is the hottest point with highest temperature in the turbine. So in terms of temperature, this point will have what I call the value of temperature can be greater than 1000 degrees Celsius. Okay, so if we can increase the turbine inlet temperature as high as possible, we will have several benefits. First, in terms of economy aspect, the specific fuel consumption will be reduced, which means we will use less fuel, but we will have high value of efficiency. So, and the benefit for the jet engine, if we have high value of turbine inlet temperature, so the jet engine will produce more specific thrust. Okay, so this is good for jet engine. However, for the industrial gas turbine, due to higher value of turbine inlet temperature, the gas turbine engine will produce more W out in order to generate the electricity. Okay, this is due to the high rotational speed that produced by hot exhaust gas. Okay, so due to the high temperature at the inlet of the turbine blade, especially at the first stage of the high pressure turbine, must be able to stand at high inlet temperature condition. Okay, so that's why we have different type of blade. So in this case, we will discuss about two type of what I call turbine blade. Okay, first we have the blade that we call cool blade. So this type of blade will have what I call the cooling system in order to what I call to reduce the temperature of the blade. And this kind of blade normally we will use for the high pressure turbine, where we have highest temperature of exhaust gas at the initial stage of the expansion process in the turbine. Okay, and this is what I call the features or the figures for the cold blade of the turbine blade. Okay, so we can see a lot of holes on the surface of the blade. Okay, we have an example of holes that what I call that fabricate on the surface of the blade, holes at the leading edge of the blade, and holes at the trailing edge of the blade. And these holes will use to supply cool air in order to form what called air film surrounding the blade profile, so that the temperature of the blade can be reduced. So the highest allowable gas temperature for this kind of cool blade, in terms of maximum, the temperature can be up to 1800 Kelvin. Okay, so the second type of blade we call uncooled blade, the typical blade without cooling system, and this blade normally we will use at the end stage of the turbine, or we call low pressure turbine, because the temperature at the stage already reduced, relatively not too hot if compared to the first stage of the high high pressure turbine. So for this type of blade, no cooling system provided. So that's why if we look at the surface, no holes available on the surface of the blade. And the highest allowable gas temperature for this kind of blade is between 1250 Kelvin to 1300 Kelvin. Turbine blade cooling in terms of fluid flow. So in this slide we will learn about the how we can transfer the cooling air from the compressor to the turbine blades. So the system of blade cooling most commonly employed in an aircraft gas turbine. So the figure shows the cross section of turbofan jet engine that consists of low pressure compressor, high pressure compressor, high pressure turbine, and also low pressure turbine. So if we zoom in, what call the part inside the pink box, so we have this figure where clearly we can see the detailed component of high pressure compressor, compressor chamber, high pressure turbine, and also low pressure turbine. So our focus in this figure is the what I call the first stage of high pressure turbine, that consists of nozzle and also rotor. So this part will experience the highest temperature of the exhaust gas. Okay, if we zoom in the part, so the part will consist of the arrangement of the nozzle blade and also the rotor blade. And clearly we can see that both nozzle and also rotor blade will use the cool blade types of turbine blades. So this type will use in order to reduce the temperature of the nozzle and also the rotor blade in the turbine. So the arrow represent the the flow of cooling air, where the red color arrow represent the high pressure cooling air that come from high pressure compressor, and blue color arrow represent the low pressure cooling air that come from low pressure compressor. So in order to observe the cooling air flow inside the gas turbine engine, so we need to refer to this schematic diagram. So this schematic diagram represent the cross-section drawing of the part of the jet engine. Okay, so the figures consist of the rotor drum, high pressure compressor, high pressure turbine, and also low pressure turbine. So for the compressor, the grey blade represent the stator or nozzle of all the compressor. The blue color blade represent the compressor, the rotor of the compressor. So we have combustion chamber and also the nozzle for the turbine. And the green color blade represent the rotor for the turbine. And also we have ducting system to transfer the compressed air into the turbine blade. And as we know, at the inlet of the turbine, the temperature of the gas of the exhaust gas at the highest condition, where the temperature can be greater than 1000 degrees Celsius. So due to the high temperature of the exhaust gas, so we need to use a cool blade that represented by CB, as shown in the figure, where this cool blade can stand the condition of the exhaust gas up to 1800 Kelvin. However, so for cool blade, we will use for high pressure turbine, because normally high pressure turbine will have highest condition in terms of temperature of exhaust gas. However, for low pressure turbine, because the exhaust gas temperature already reduced, so the blade type that we will use for the low pressure turbine is uncooled blade, the typical blade without cooling system. And the temperature that can stand by the blade is around 1250 up to 1300 Kelvin. Okay, there are two types of cooling air that we'll use in the cooling system. First, high pressure cooling air that come from high pressure compressor. And the second one is low pressure cooling air, where the cooling air come from low pressure compressor. Okay, so in terms of from the high pressure cooling air that produced from the high pressure compressor, the cooling air will enter the combustion chamber and also will flow through the passage outside the combustion chamber. So in order to the cooling process, in order to I call to make the cooling process occur in the gas turbine engine, so there are few passage in the component of the gas turbine engine that used to allow the what I call the cooling air to pass through the component in the gas turbine. Okay, so for this case, the high pressure cooling air will enter the first nozzle of the high pressure turbine from the bottom and also from the above of the nozzle. And this what I call these features depend on the design of the blade. And the high pressure cooling air also can enter from the bottom of the rotor blade of the first stage of the high pressure turbine. Okay, so for the second nozzle of the high pressure turbine, let's say this nozzle will use two type of cooling air. First, for the what I call high pressure cooling air. The second one is low pressure cooling air. So for this nozzle blade, will have two type of passage. First, the passage for high pressure cooling air. The second one for the low pressure cooling air. Okay, as shown in the figure. So the high pressure cooling air will enter from the bottom of the nozzle. Okay, for the low pressure cooling air, the cooling air will come from actually from the low pressure compressor, where this cooling air will flow through the ducting system, and the temperature is approximately around 400 degree to 450 degrees Celsius. So if you look at the value, the temperature already high enough. However, if you compare to the temperature of the exhaust gas in the temperature, so this temperature of the low pressure cooling air is considered as low. So we can use this low pressure cooling air from the compressor to cool down the turbine blade. Okay, so the low pressure cooling air will flow through the ducting system and enter the first nozzle for the low pressure turbine. Okay, and flow through the nozzle and enter the second nozzle of the high pressure turbine from the nozzle, as shown in the figure. And this low pressure cooling air also enter from the bottom of the second rotor blade of the high pressure turbine. Okay, so this is how the cooling air flow throughout the gas turbine blade cooling system. So in order to look in detail what I call for the cool blade we call type blade turbine blade. Okay, we take the what I call the cooling air passage in high pressure turbine rotor blade as shown in the figure. So the figure shows the cross section of the cool blade type of turbine blade. that consists of two type of passage. The passage with red color passage represent the passage for the high pressure cooling air, and blue color passage is for the low pressure cooling passage, low pressure cooling air passage. And the air emerge with little velocity and form a film of cool air around the blade surface as shown in the figure. So this process will form a cooling film surrounding the blade and act as insulation. So this process will insulating blade surface from the hot gas, and the temperature of the blade will reduce as shown in the figure. The figure shows the simulation result where we can see the red color area represent the hot region, and the green and blue region represent the what I call the low temperature surface after the cooling process due to the formation of cooling film. Okay, so the line in the figure shows the cooling air film. So there are a few disadvantages for this process, because in order to pressurize the air bleed off from the compressor for cooling process, we need to supply some energy, and when we supply some energy, this will affect the gas turbine efficiency. So the efficiency of the gas turbine will slightly reduce. Okay, in order to look the effect of cooling system to the turbine efficiency, so we need to consider called the turbine blade cooling penalty that obtained by Wilde 1977, that show the result in terms of turbine thermal efficiency versus inlet gas temperature. Okay, as shown in the figure. So the figure shows the graph in terms of relationship between efficiency of the turbine versus turbine entry temperature. So in the graph, we will divide into four regions: first region, second, third, and also the fourth region. So there are two curves involved in the graph. The first curve that represented by blue color line is called the efficiency curve for low hub to tip ratio turbine, and the dashed line for the blue color line normally represent the what I call the expected result for the low hub to tip ratio. The second line or second curve is for the efficiency for the high hub to tip ratio. Okay, so this figure shows the difference between low hub to tip ratio and also high hub to tip ratio. So in terms of easy to understand, so low hub to tip ratio will give you the shorter blade height if you compare to the high hub tip ratio. Okay, so for the temperature from the 1200 Kelvin up to 1300 Kelvin, normally we will use the uncooled blade as shown in the figure. So no holes for the cooling process. So the type of engine that use this kind of blade are Conway jet engine as shown in the figure, and also Spey jet engine. And for this type of engine, in terms of temperature, entry temperature, and also the efficiency is around, the efficiency is around 90%, and the entry temperature, inlet temperature of the turbine is around 1215 Kelvin. Okay, for the second type of blade, which is more advanced if compared to the previous one, is the internal convection cooling, that as shown in the figure. So we have cooling passage inside the blade, and this blade, example of this blade is for the single pass internal cooling. Okay, the type of engine that use this type of blade, cool blade, are the Adore engine, where by using what I call the engine will have In terms of efficiency, 85%, and inlet temperature is around 1392 Kelvin. And second one is RB211 engine. And the efficiency for the engine is around 83%, and the entry temperature is 1556 Kelvin. The third type of blade we call internal convection and also film cooling. So this type of blade use two different type of cooling process. First, internal convection, and the second one is the film cooling process. So we will have a lot of holes on the surface of the blade, and also we have internal passage within the blade. Okay, so from the result of the welding, so at this moment in 1977, clearly we can see that no engine jet no engine jet that use this kind of blade. So this kind of blade is still under investigation during that time. So we only get the result for the engine in terms of engine test that use the internal convection, also film cooling blade type. Okay, so the efficiency is around 80%, 78% to 80%. So you can see that if we use more advanced call the cooling process for the turbine blade, where involve more cooling air, we can see that the efficiency reduce. Although the turbine inlet entry that can stand by the blade increase, however the efficiency keep reduce. Okay. Okay, the last type is transpiration cooling blade. So this type of blade is a new invention in terms of blade cooling system. Okay, so the air will come out from the blade surface due to the porosity of the material that used to make the blade. Okay, to check your understanding for part 7, chapter number 4, answer the question below. First question, why do we need to use cold blade? Second question, which specific section in a jet turbine engine required the usage of cold blades? Question number 3, if we use more advanced cold blade, the gas turbine efficiency will decrease more. Why? Give your opinion. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 7, chapter number 4. Assalamualaikum.